The Extended Deep Energy Method XDEM, a unified AI framework for fracture mechanics. Introduction. Fracture mechanics stands as one of the most challenging domains in computational mechanics, with accurate prediction of crack initiation and propagation remaining a central problem in engineering and materials science. Traditional computational approaches have evolved along two distinct trajectories: discrete fracture models and continuous damage models. Discrete approaches, including the virtual crack closure technique VCCT, cohesive zone method CZM, and extended finite element methods XFEM-XIGA, offer computational efficiency but require explicit crack representation and fracture criteria, making them difficult to apply to complex crack networks. Continuous approaches, such as the phase field method and peridynamics, provide greater flexibility by allowing cracks to nucleate and evolve without explicit tracking, but at the cost of significantly higher computational expense due to fine spatial discretization requirements. The emergence of physics-informed neural networks PINs and the deep energy method DEM has introduced a new paradigm for solving partial differential equations by embedding physical laws directly into neural network training objectives. While DEM has shown promise in fracture mechanics applications, existing approaches face several critical limitations. They require dense collocation near cracks, suffer from stability challenges, and treat discrete and continuous fracture models separately. The Extended Deep Energy Method XDEM, proposed by Wang et al., addresses these limitations through a unified AI-driven framework that seamlessly integrates both formulations. Core innovations of XDEM. Unified Framework Architecture. XDEM establishes a single variational framework applicable to both discrete and continuous fracture models. In the discrete regime, the method introduces a crack function to represent displacement discontinuities and an extended function to capture near-tip asymptotic fields. In the continuous phase field regime, XDEM decouples displacement and damage evolution through flexible neural architectures, enforcing irreversibility via penalization or history field strategies. This integration eliminates the need for problem-specific collocation refinement while substantially enhancing accuracy, robustness, and computational efficiency. Discrete formulation. The discrete XDEM formulation builds upon the energy-based loss functional, pi equals UE, WEXT, where UE represents elastic strain energy and WEXT denotes external work. Specifically, WEXT quantifies the work performed by externally applied forces such as surface tracked ions and body forces on the deformed solid. Mathematically, it is expressed as WEXT equals indefinite integral omega bud omega plus indefinite integral gamma underscore ttud gamma, where B denotes body forces per unit volume, T represents prescribed tracked ions on the Newman boundary gamma underscore T, and U is the displacement field. In the total potential energy functional pi equals UE, WEXT, the external work appears with a negative sign because the potential energy of the external loads decreases as the loads move through the displacements they cause. Consequently, minimizing pi with respect to the displacement field enforces the principle of virtual work. The variation of the internal strain energy delta UE equals the variation of the external work WEXT, which is precisely the weak form of the equilibrium equations. This formulation ensures that the neural network's predictions satisfy both equilibrium and traction boundary conditions in an energy-consistent manner without requiring explicit collocation of traction-free conditions on crack faces. The identical definition and physical interpretation of WEXT apply to the continuous phase field formulation pi equals UE plus UC, WEXT, where the external work remains coupled to the displacement field through the same integral expression. The key innovation lies in representing displacement discontinuities through a crack function ρx that satisfies specific conditions across the crack surface. This crack function combines a sine function with distance-based terms to embed discontinuity information directly into the neural network architecture. Furthermore, XDEM incorporates the Williams series expansion to capture near-tip singular fields through an extended function. This enrichment enables accurate representation of stress intensity factors using sparse, uniformly distributed collocation points, a significant departure from traditional approaches requiring refined meshing near crack tips. The extended function includes a decay term to appropriately weight the asymptotic solution's influence away from the crack tip. Continuous damage formulation. For continuous fracture modeling, XDEM employs a phase field variable to represent cracks, with separate neural networks approximating displacement and phase fields. The loss functional incorporates both elastic strain energy and crack surface energy, pi equals UE plus UC, Wext, where UC represents the energy associated with crack formation. The method recommends using radial basis function RBF networks for the phase field and Kolmogorov-Arnold networks GANs for the displacement field, leveraging the respective strengths of these architectures for handling sharp variations and complex functional relationships. Transfer learning via LoRa. A particularly innovative aspect of XDEM is the integration of low-rank adaptation LoRa for efficient transfer learning between load increments. Since fracture simulations require discretizing the loading process into multiple steps with strong correlations between successive fields, LoRa significantly reduces computational cost by approximating weight updates through low-rank matrix decomposition. This approach reduces trainable parameters from DM to RD plus M, where R is the rank typically set to 1 in XDEM, enabling rapid fine-tuning while maintaining accuracy, validation and performance. Stress intensity factor prediction. XDEM demonstrates exceptional accuracy in predicting stress intensity factors SIFs across various fracture modes. For mixed-mode crack problems, the method achieves relative errors below 1% for both key and key components with moderate collocation densities. The results show consistent convergence as collocation point density increases, with 80 times 80 points typically sufficient for high accuracy across crack inclination angles ranging from 15 degrees to 75 degrees. The method's robustness extends to complex crack topologies, including intersecting cracks with varying angles. XDEM accurately reproduces displacement discontinuities along multiple crack interfaces, validating its capability to handle intricate crack networks without requiring adaptive meshing or problem-specific refinement. Crack propagation simulations. XDEM's performance in simulating dynamic crack evolution is demonstrated through 3 representative scenarios: straight crack growth, crack kinking, and crack initiation. The classical Bittencourt problem, a widely used benchmark, shows XDEM accurately reproducing experimentally observed crack trajectories, including the deflection toward holes depending on initial crack position. The predicted crack paths show excellent agreement with both experimental observations and established numerical results. For problems involving material heterogeneities, such as stiffness inclusions, XDEM demonstrates robust performance in capturing crack interaction with different material properties. The method accurately predicts crack trajectories for both soft and hard inclusions, and the low displacement responses show excellent agreement with reference solutions. Advantages over conventional approaches. XDEM offers several significant advantages over traditional computational methods and standard DEM formulations: elimination of collocation refinement, by embedding crack discontinuities and asymptotic fields directly into the neural architecture. XDEM maintains high accuracy with uniformly distributed sampling points. Unified treatment. The method seamlessly bridges discrete and continuous fracture models within a single framework, enabling practitioners to choose the most appropriate formulation for their specific problem without switching methodologies. Computational efficiency. The combination of energy-based formulation and transfer learning significantly reduces computational cost, particularly for multi-step fracture simulations. Enhanced stability. The variational formulation and strategic architecture choices improve numerical stability across a wide spectrum of fracture scenarios. Complex topology handling. XDEM naturally handles complex crack networks, including kinking, branching, and coalescence, without requiring special treatment. Broader implications and future directions. XDEM establishes a scalable foundation for AI-driven computational mechanics, with implications extending beyond fracture simulation. The unified structure, variational grounding, and compatibility with transfer learning techniques position it as a powerful framework for large-scale simulations of complex materials and structures. Future extensions could include dynamic fracture, multiphysics coupling, thermomechanical or fluid-driven cracking, and neural operator-based generalization. The integration of transfer learning could be further refined to improve integration accuracy in later load steps, and the framework could be adapted for probabilistic fracture modeling and uncertainty quantification. Conclusion. The extended deep energy method represents a significant advancement in applying artificial intelligence to fracture mechanics. By unifying discrete and continuous formulations, eliminating problem-specific collocation refinement, and leveraging efficient transfer learning, XDEM overcomes long-standing limitations of conventional approaches. The comprehensive validation across canonical benchmarks demonstrates that XDEM achieves accuracy and efficiency on PAR with, and in many cases surpassing, traditional numerical methods. This work exemplifies how physics-informed AI can transform predictive modeling in engineering and materials science, providing a robust foundation for future developments in computational fracture mechanics.